So Hugo, actually, he did his master and PhD here in São Paulo and postdoc. He's leading the harmonic space analysis in dark energy survey with Felipe Andrade Oliveira and Lucas Fasta. Lucas is coming maybe today.
Maybe, let's see if
Maybe.
Yeah.
And then Hugo was a big fan of Pink Floyd, so he decided to work on the dark side of the moon.
Yeah, that's the main reason.
So he's now working Brookhaven with Schlosser, and in this project called Lucy Night. So he's going to tell us all about
When I try.
Lucy Night and intensity map in far side of the moon.
Yeah, no, thank you so much. Thank you so much. And thank you so much to everybody here. It's a pleasure to be here, you know, like on the other side. I usually
On the other
always
side of the moon?
on the other side. Well, I don't want to be there. So yeah, I will try to give an overview of this pretty interesting project. It sounds like science fiction, but it's quite interesting. So let's see if I manage. You can interrupt me whenever you want.
Don't worry.
Let's see. I know you will. Let's see if this is changing. Yeah. So yeah, just a quick overview. So the thing is, okay, we're talking about cosmology. So not sure if anybody has been talking about this thing, but I will talk about Dark Ages cosmology, which is the main motivation of this kind of project. I will do this history and context of this radio instrumentation on the moon or around the moon. And I will talk about this thing that we've been doing with Andrew, which is this basically the map making for these kind of instruments, you know? So, okay, so Dark Ages. So basically, the main idea is there's this.
So there should be a ruler somewhere.
I didn't see it. No, I can do it with my hand. So basically, we have this study, you know, there's this open window that is one of the less explored observations of the expansion of the universe, which is in between recombination, basically the formation of the first stars, whatever this age is. And it's around like redshifts of some tens to some hundreds or something like that. People call it dark ages because you still do not have like compact objects emitting light or something like that. And it's basically dominated by neutral hydrogen. So you probably, so the thing that we have there is we already have neutral hydrogen. It's basically plaguing all the universe. So it's quite interesting because in principle, we believe that it should be like well described by linear physics because you still do not have basically compact radiation sources. And because of the same thing, we basically do not have any optical radiation to observe now. And so, yeah, so this defines what the dark ages are. So this thing you probably already heard about this story of the 21 centimeter emission from neutral hydrogen from Jose Luis. But I'll just briefly describe it again. So how can we observe neutral hydrogen? So there's this really interesting transition, hyperplane transition in the neutral hydrogen atom, which is basically the spring flip of the electron that is pretty prohibited. So it will show like a pretty sharp feature on the spectrum. And it is really well known to be like with a frequency of 1,420 megahertz. And this corresponds to some 21 centimeters. That's the reason that people call it like that all the way down now. So the thing is, okay, this is super sharp. Is the only thing that you can only have there. It's pretty interesting that in order to see this kind of thing, you really need atomic hydrogen. You cannot have like ionized or molecular hydrogen to have this kind of thing. No. So this thing can be observed in various stages of the universe. But in principle, this is like the observational window to look at dark ages because in there you have pretty neutral hydrogen plaguing the universe. No? So yeah, so this is like to put it in context. People must, like in recent literature in the recent times, people have been talking about this thing to do intensity mapping. So I'm pretty sure Jose Luis talked about this thing. So you should hear about this thing. So doing things with neutral hydrogen at low redshifts, so basically of order 1 or something like that. After we have some formation right down. Basically, you have these pockets of neutral hydrogen. You can do things like line intensity mapping. I won't say anything about that thing, but anyways, you should know by now. But we also have neutral hydrogen in other epochs of the universe. So basically, near the ionization, you also have because of the first stars are beginning to form. You have these large bubbles of ionized gas. So you should have different kinds of structure of neutral hydrogen between them now. So the thing that I want to highlight is basically in dark ages, this is mostly the universe is neutral hydrogen. So you're basically looking at the pristine or primordial density field of basically the whole matter in the universe. So it's basically should allow us to map the universe. I mean, if you can measure 21 centimeter light coming from this circle, you're basically looking at all the structure of matter in the universe in some sense. No, I will discuss a little bit more about that thing, but in here you will do something different. No? And this is pretty cosmological. These two things are pretty astrophysical processes dominating how the neutral hydrogen is distributed now.
So the relation between neutral hydrogen and dark matter is like one. It's like the bias is one.
So in principle, yeah, it should be pretty. It should be more or less like that, because basically the universe there is mostly dominated by neutral hydrogen. So, but the thing is that this is something that haven't been explored. So the first thing to do is, or the first observable to look for is something similar to the history of the CMB now. Like people know that cosmic microwave background radiation should exist. And the first thing that you look to do that detection is basically the monopole, which is basically the mean temperature of the whole CMB in the entire sky or something like that at some specific frequency. No, this is the first thing that people wants to do for dark ages, is basically to measure the monopole of the 21 centimeter emission from the dark ages, neutral hydrogen. And so here what I'm showing is like, what people believe is like the monopole, like the frequency dependent monopole in terms of brightness of 21 centimeter in temperature as a function of frequency. And here we also have redshift, like for reference. And the thing that we are very interested is this one, which is basically, we see pure hydrogen, as I was saying, in contrast with CMB. So basically what is happening is CMB photons are basically being absorbed by the neutral hydrogen. And the thing that they are doing is this flip of the electron and the emission of the 21 centimeter light. So this process is the thing that we see here, like this throw here. And this is the main thing that people want to see we are able to detect. After that, there are
two. Sorry, it's an absorption line because you're having a dip in the pressure.
So it's not specifically a line. It's basically a broad throw between different frequencies.
And that's because of this. So this is the CMB.
It's basically the CMB is shining the neutral hydrogen, which is basically the universe at that epoch.
Yeah.
And then this through is basically the 21 centimeter radiation coming afterwards, because we have every kind of radiation that we can detect, but here we are only measuring the 21 centimeter radiation with some kind of instrument that I will describe later. So if you only look at that frequency and you try to see how the thing is distributed, it should look like these kind of things. So it should have like a
You said before that the frequency of 21 centimeters 1400 megahertz.
Yeah.
And there
it is scaled, but it is scaled basically. So it is at rest now, but the universe is expanding.
Oh.
So we see this thing changing in frequency. If the photon was measured like near redshift 100, which is dark ages, we will see the 21 centimeter line at around 20 or something like that megahertz. But we have neutral hydrogen plaguing the universe all the way down the cosmic history. Now this is like the spectrum of 21 centimeter being emitted like during the entire history of the universe. And you are looking here like in frequency or in redshift. And this is basically scaling that 1,000 megahertz in redshift.
So 0 is CMB, the temperature of CMB.
Yeah, more or less.
Can you see this absorption? Can you see some kind of distortion, the CMB, like the white surface?
Yeah, I think that's possible. That's also possible. With this, I mean, here there should be fluctuation because this thing I will mention. Yeah, I will come back to that. And so, yeah, the main thing here is, okay, this is still not detected. This is what people expects that it look like, and there are like 3 different processes that are important here. One is the absorption and emission of CMB photons, and basically in dark cages, the absorption of CMB photons should be dominant, is what people expect. And there are other things. So, for example, when heating begins, there should be like basically resonant scattering of light and alpha photons. But basically, after this thing, everything is basically astrophysical processes and way more messy than this dark cages part, which is basically cosmological linear physics in principle, or at least we hope so. No. And so yeah, this is maybe what I want to say here.
But you said that in order to have the 21 centimeters, you cannot have the ionized hydrogen, but
There is
ionization begins, you have a more.
Well, but basically you still have neutral hydrogen all the way in the history of the universe, in less proportion, but you still have. Actually, the universe is mostly hydrogen.
Right, but why when ionization begins, you have this excess?
This excess? So there are, yeah, I fully not entirely understand the astrophysical processes happening there, but I know that there you usually have like collisions with other particles, and there's like reheating by collisions or something like that.
So you have the heating of the
Please help me.
The
Exactly.
heating?
so like the gas that emit X-rays
Yeah.
and to heat
Exactly.
a lot without like on top of like the ionization,
Yes,
there's also like once all those ionizing photons have been absorbed, there are also like heating
yeah.
on the neutral gas, and then that's heated over the CMB. Like the spin temperature goes over the CMB temperature, and that's why you see it.
But not 21 centimeters.
Yeah, not it was limited because like there's like
So
no, but like you mean like what you're seeing here is a 21 centimeter line.
Yeah.
Of like the neutral hydrogen
Yeah.
have been heated emitting the hyperfine transition.
But the X-ray should be totally independent
That's
of
it.
21
maybe
centimeters.
Oh yeah, no, like this is like you would see like if you observe in the X, you would imagine that like those X-rays will arrive here, you have like enough like with enough
Yes.
telescope, you would observe that.
Yeah.
But in radio,
you will do
you
it.
see the emission of the 21 centimeter cooling after it has been heated.
So Roger, maybe another way of understanding this is you're basically measuring the temperature of this thing, because it's like the monopole brightness of this thing. It is like the monopole of the CMB. The natural analogous is this kind of thing. So you can think on what kind of process can basically give more temperature to this kind of one. And it's things like what one Jose Luis is saying.
And to explain why during the dark ages it's down and then
So it is so the thing that basically is giving is changing the temperature there is basically absorption of CMB photons, which is causing like the spin temperature as Jose Luis was saying. That is the thing that is causing the flip. Is mostly interaction with CMB photons, basically interacting with neutral hydrogen, and this thing is basically absorbing energy. It is like a calorimeter. This thing.
first is down and then
Exactly. After, so the cooling down is basically because the thing is it is absorbing energy from the CMB photons. Then the temperature of the spin temperature of neutral hydrogen should go down. You can think of this as the net temperature of the spin temperature of neutral hydrogen.
So now I think I understand better. So it's not a black body temperature. It's a spin temperature.
Yeah, exactly.
Which is given by the ratio of hydrogen in one state and.
Exactly. It is so in some sense, this thing works like a calorimeter. It's like it can absorb some kind of energy and then basically change temperature, and it can emit and then also change the spin temperature.
Spin temperature.
Exactly.
Now it makes more sense.
So I will say something more about that. So basically, this dark ages monopole is what we are saying. It's basically a cosmic calorimeter. And so this is like for theory people on the audience that I know there's a
Sorry,
bunch.
so cosmic, can you say again what do you mean by cosmic calorimeter?
So it's basically a calorimeter is something that can give you like yeah, basically you're measuring changes in the mean temperature on the spin temperature of neutral hydrogen. So whatever can change that temperature, you can see it on the monopole.
Okay.
So if we really understand thermodynamics by that time of the universe, we can explain that kind of monopole. And if there's anything that we don't know, it should be seen there. So that's the thing that I want to say on this slide. So people,
spin temperature.
yeah, so people
Now it's
think,
spin temperature.
exactly. So people think that, okay, there should only be like CMB photons. If there's only CMB photons, you should see the true there. But any modifications of this true should be like in this, should be an indication of additional things that maybe people already know, but haven't seen, but haven't been possible to be detected. So it's things like opening a new window to look for different things. So the thing is, for example, for people thinking on theoretical descriptions or deviations from thermodynamics of the early universe, there's a whole suite of things that I'm not an expert on these kind of things, but there's a whole suite of things that you can begin to think to look into this. If some kind of detection of the monopole of the 21 centimeter die from dark ages can be done. So
what you observe today is, but from the wavelength, you can see what is the redshift, basically, you know. And then you can check if you're looking at the dark ages or intermediate ages. That's the idea, right?
That's more or less the idea. So the first thing is, so maybe I keep going to this analogy, but this is the nicest thing that I can think. It's basically looking at the monopole of the CMB temperature is what Kobe did. So it's basically, okay, we understand how CMB photons are distributed. Yeah, we expect that this thing looks like a black body radiation, no? Any deviation from that black body radiation, the first detection of the CMB should give you some hints about, okay, maybe we don't understand entirely the physics of the CMB photons. This is more or less the kind of situation that we are here is, okay, can we measure the spin temperature of neutral hydrogen on dark ages? Maybe there's people, this is what I'm going to talk about.
As a function
And if we can do it as a function of
angular separation.
no, it's still not any.
It's monopole.
It's the monopole only. This is only the monopole. It's like the mean temperature on the entire sky. So this is the first thing. So it's interesting that this thing is basically highlighting this decadal survey on astronomy and astrophysics. So it is highlighted as a discovery area, no, because it is still not explored. Is the instrumentation super complicated? But people are still there are multiple groups working on this kind of instrument to do this kind of measurement. So yeah, this is more or less the motivation. No? So again, just doing a brief summary. So what we are trying to do is basically come up with instruments that can do this kind of measurement and working that as a cosmic calorimeter. It's basically that kind of stuff. This is just to give a.
So what? Sorry, I'm trying to understand again the dip in the dark ages. Why the CMB is actually decreasing
The mean temperature.
the mean temperature?
Because basically the thing that is happening is the CMB is the one that is causing the flip on the.
It's causing the flip.
Exactly.
It's inducing the flips, not
Gas is called there. Because the gas go like cruise as like 1 plus C square rather than 1 plus C.
yeah.
Well, that's another way to.
And then there's like collisional coupling between the CMB photons and the hydrogen. And that's why there's like an energy transfer from the CMB photons to the.
So it should warm up.
No, you're seeing that over the CMB spectrum. So the CMB spectrum goes down. Do you remember the plot that I saw the other day that you had the black body from the CMB and you had a dip and then going up? So like that's that dip in the CMB spectrum.
Yeah.
Because you will see on that as a spectral distortion basically on the CMB.
But for the CMB, that's for the.
No, like
No,
like the zero level
it's
is the CMB.
yeah.
The model.
But again, this is the spin temperature. It's not.
No, this is like the brightness temperature.
Ah.
That this is the brightness temperature of the 21 centimeters that depends on the spin temperature.
We can talk later.
And then like when it goes out is when like this collisional coupling starts
begins to be inefficient. Yeah, it's like.
Now I remember. Okay, thanks.
Yeah, thank you. So yeah.
Since this effect impacts the CMB as a spectral distortion, is there any prospect to measure said spectral distortion on the CMB?
Yeah.
Like the XM, no?
Yeah. I think that yeah, there are prospects for doing that. I know there are papers doing that thing. I can show you papers about that thing. So I'm not an expert on that, but yeah, I'm aware of these kind of things. So yeah, what I want to tell you is what do we need to measure these kind of things, no? So basically going back to this figure, basically this dark ages should be like this 21 centimeter emission line or whatever. This should be it should fall between tens of megahertz.
Right.
And this is basically a radio frequency, the standard radio frequency that we use, for example, here on Earth for doing communications, and your cell device also work on that. So it's basically RFI. So it is what we called in the radio frequency spectrum like the frequencies that we use for radio communication. So in some sense, people have been arguing because of that it's impossible to do from Earth because everything is basically noise, and this kind of measurement should be basically impossible. There is all the noise that every an anthropogenic device is basically generating, and there's the other fact that the ionosphere, it's also refracting and reflecting at the same frequencies. So basically we are in a cage that is basically plaguing of noise, any kind of measurements on that frequencies, no? And so people have been dreaming on how to do these kind of things, and one of the solutions is basically doing this thing on some place on the space that is somehow radio quiet. And one of the possibilities is basically on the far side of the moon, and using the moon as like a blindage system for radio frequencies. Why we believe that? So there are things that we know about low radio frequency on the sky. This is a really interesting story. So latest data of radio from that frequency is basically from the 70s. And it's come from this Radio Astronomy Explorer 2. There was like a mission that was sent to space to do basically, it was like a Pathfinder to do measurements on that kind of frequencies. And it basically orbited the moon at some point of his journey. And this data is actually from that thing. And it's like, basically you have here relative angular temperature, which is the kind of measurement that we want to do. And here you see like two things, like immersion, which is actually being like going back on the moon with respect to us, and immersion, which is coming back from the other side with respect to us from the moon. So the thing is that this data from the 70s suggests that actually the moon is blocking most of the frequencies that we are interested in. So this is like the main thing that people have been saying, that we have evidence that the moon can be worked as really as a blockage in these radio frequencies. So yeah, there's been like this universal time, this thing flow in the 70s. And this data comes from 1973, the same time that the dark side of the moon was released. And this data is still available. There's actually people looking at this. I've been looking at this data, doing other things. But whatever. And so it's quite interesting that the only data that we have from the sky at that frequency is from the 70s. So in some sense, these kind of projects are also looking like to update these kind of measurements. It's like time to do something better than what we did on the 70s. And the other thing I wanted to highlight here is
But this is still orbiting the moon?
No, this it's basically decommissioned at some point. No. I think it was so this thing was intended to do various things. One thing is it was an orbit like going around the moon for some time and then going to see the sun for some time, and it basically disappeared. But most of the data, most of the important data was actually of this thing is for solar physics program.
Quiet, but doesn't block you from reading from the Earth. But what about astrophysical sources?
It shouldn't be radiated from astrophysical sources. But the whole point is at least to take out the noise from anthropogenic sources, let's say. Because you can still see astrophysical sources there. Obviously, I will talk about this thing. So astrophysical sources is actually what I wanted to say here. So here you have like the most important thing, which is actually the galaxy. The Milky Way is basically the main thing that is emitting at that kind of frequencies is synchrotron from the center of the galaxy. And basically dark ages signal at that frequencies is orders of magnitude below the synchrotron from the center of the galaxy now. So singleton from the center of the galaxy is something of the order 10 to the 6, and it should be like a power law, people believe. These measurements actually comes from this data from the 70s. Actually, this power spectra for the singleton of the center of the galaxy. You have the CMB. The CMB at the same frequency, you can also look at that, and it should look like a reference. No, and it is also like at least 2 or 3 orders of magnitude above. But the CMB we know, so this is okay. But this thing is super complicated. Now, this is like the main thing that we should be aware if we try to extract from some kind of sum of all of these effects and extract only this signal. So yeah, so this is like the map of the thing. So think of Lucy. So let's see if I can do this thing. So think of Lucy is like the US way of having this kind of thing on the way. And the thing is basically, this is a study of using a SpaceX as a carrier system to send some payloads to the moon. And basically the US is in this process of doing this kind of thing, like a precursor of this Artemis project, which is intended to send people to the moon. But the first thing before that thing is something that they call CLIPS, which is this commercial lunar payload services that is sending like private stuff, but they also have some funding for sending science stuff. So there has been 2 senders there that basically they called like commercial services, CS, and I will say something about the thing that got some attention by the beginning of this year. And so the thing is, there are some independent business that basically SpaceX works as the thing that sends the rocket. Some independent companies basically propose ways to land on the moon, and these are the commercial services. And inside these landers, many people can do stuff, and in some of them there can be like science payloads. And the story is more or less for Lucy. So okay, I will say something about this thing. Well, yeah. So the story for Lucy is the Space Science Laboratory like was awarded to be like one of the scientific instruments that can be on board of some of those commercial services. And they originally think on doing some solar astrophysics, like an instrument to do solar astrophysics. But then the DOE enters with this program of looking at dark ages as a discovery thing. And basically do this synergy of the DOE 21 centimeter cosmology program with the award we think of the UC Berkeley. And they came up with this concept of sending something that can do both things. So basically focus some kind of payload to have some time to do solar science, and have some other two that are intended to do some kind of 21 centimeter science. And those are like Lucy 9 and some perfect calibrator that I mentioned a little bit also in this. So those two things are basically commercial services 3 and 4. And by now, we've been seeing happening the commercial service 1 and the commercial service 2, which are things that happen in January and in February of this year. Now the Astrobotic Peregrine and the Intuitive Machine Odysseus, that were I should say that they were like not exactly so they didn't succeed now. So basically the study is with this thing, they have some problem with the engine, and it couldn't make it to the moon. And with this thing, it actually go to the moon, but it flips on the side, the lander. This one has like an instrument to do precursor radio measurements of the regolith of the moon that will gonna be used by Lucy afterwards, but it couldn't be done because of many reasons. So many things happened wrong in this mission, but none of them was totally catastrophic. So these people learned a lot with this kind of stuff. And so the thing is
insurance?
no,
No insurance?
no, no insurance.
But
So
it was on the dark side of the moon? Or
no, none of them were targeting the dark side of the moon. So The other thing is for Lucy, the budget is more or less, so this thing is fully funded. This is interesting.
It's only DOE?
It's only DOE, it's DOE plus NASA. And it's gonna be on the next one. So yeah, so now I want to say something about the science goals of this kind of project. So basically, the way that people is conceiving this thing is basically the first goal is to show that we can actually do a kind of measurement of these on these frequencies on the moon. So it's basically establishing the lunar surface as a viable way to do this kind of measurements for the first time. And then the other science goals are like a little bit more ambitious, and it's basically to perform these most sensitive. It's basically to update the things that Ray did in the 70s, and have like an absolute calibration of 20% on the spectrum at these frequencies. And obviously to quantify the systematics affecting these things. So basically have a way to measure actually, or to disentangle, for example, the synchrotron radiation from the center of the galaxy. And if everything goes well, to constrain the presence of this smooth monopole, which is at the level of 10 to the -3, as I was telling you, on the overall power spectrum at these frequencies.
Can I ask a naive question? So, as you said, no, the far side of the moon is not a dark side because you get sun sometimes,
Of
right?
course, yeah.
So when it's illuminated by the sun, the sun also gets in radio?
Yeah.
So that's a big problem. Can you make observations?
Yep.
Also when it's
The sun also emits at these frequencies, but in principle, so the instrument can take data. I think this is still open. I mean, it can take data, but the main thing during that phase is basically recharge batteries.
is what, sir?
Is recharge the battery, because the thing is going to. So I will mention a little bit about the thing, but the main thing during this lunar day is actually to recharge the battery of the things. Yeah, because the idea is that it will survive more than one night and take data for more than one night. But if it survives just one, the data would be somehow enough. But it's completely complicated.
The 50 megahertz, which is what you expect from the dark ages, right? It's exactly why you have all the TV radio stations here, right? So you don't have that from the sun. This, right?
Yeah, well,
Not so much.
but there's something. I think people that do solar astrophysics.
Because of magnitude less, no?
It's basically plasma, I think, also emits at this kind of.
But in terms of how much, probably much less.
Is much less, yeah. But you can also measure it if that's useful for people that do solar astrophysics. That's the point.
Sorry. Let's go in the next slide.
I think no.
So you expect components of 10 to the -3?
Yeah. So
Is that because you can reach that, or is it because you expect some physics?
it's basically this kind of expectation. So the thing is, basically how buried is this kind of feature on the overall spectrum. So the overall spectrum that people will measure will be like a sum of all of this stuff. No, there should be the CMB at that frequencies, but there should be like synchrotron from the center of the galaxy. And in order to have like a measurement of this through here, which is the same through that I was showing before, just that different scale, you have to have a precision here of at least 10 to the -3, something like this. Is basically that. So yeah, so I can say, so maybe this thing is a little bit technical, but the instrument is already designed, and so the main thing is this thing has a predefined budget, and it will reuse some things that were used for doing like solar astrophysics, particularly solar Parker stuff. And the main thing is, okay, the instrument is basically for spacer antennas. This spacer antenna is basically technology to deploy antennas. So it's basically they are going to be like packed, and when they land, they will be like released. Now, and these 4 antennas are basically 4 dipole antennas. And what we can do is basically these things can measure radiation that is incoming at that kind of frequencies. So the size of these things is of the order of some meters. And basically, the thing that we do is a radio spectrometer. So basically, the thing that we want to do is basically to correlate the signal from the 4 antennas and to use this correlation as a radio telescope. So yeah, so the idea is this thing will be launched on next year on December 2nd, and it will land on the moon on the 11th of January of 2026. So the thing is becoming increasingly real. So the CS3, this Commission Service 3, is actually been awarded to this company Firefly, and the lander is going to be called this Blue Ghost 2. And yeah, like by the beginning of this year, they're gonna begin like saying some details about these kind of things because they are already calling like the media to cover different parts of this thing. So you will probably hear more about this thing in the media.
So I don't, so there's X, the launcher will be
Yeah, the rocket is SpaceX.
SpaceX. And then what is Firefly Aerospace?
So basically, those are like the companies that are designing and building the landers. So it's like on these other two that happens this year,
Yeah.
there were two, like there were like Intuitive Machines and the other one. So basically,
another company.
yeah, exactly.
And these guys have experience with landers?
Yeah, they have some experience, but they also have as less experience as these others. They are also learning about these things. Yeah, there are many things that can go wrong. So don't worry. So
But it goes wrong, do they have to launch another one? At the
They-
contract, until they get it back?
there are various. So this is like a learning process, I think. They are basically they know that basically all of these things are not failures, but like learning process on how to do this kind of stuff. So we hope that this one will do it. I mean, someone already arrived to the far side of the moon. The Chinese space agency already put the Chang'e there. And they also have an instrument. I think I have a slide for showing something about this thing. So there's some success that is extremely complicated. I mean, there are many things that can go wrong.
But didn't they mention the radio when they went there?
It's completely noise dominated. I will show it, I think. So just to mention some of the big changes of an instrument like that is basically what you were saying. Basically, the lunar day is burning hell, and the lunar night is basically freezing. It's from hundreds of Kelvin to almost zero.
How many hours per forget? Is the lunar day?
It is of the order of days, no? Of solar days. So basically, the thing is, the 4 or 3 things that are super complicated is basically this thermal management, that it has an extremely interesting design. The power management, that it's basically, okay, the battery has to survive, but it is constrained by the size and the weight and everything, because it should be packed on this kind of, by everything that the lander specifies. There should be a problem there's also a challenge with data transfer and also with antenna performance, because we want that this thing has like a resolution 10 to the -3 to this kind of measurement. No? So maybe the only thing that of all of these problems, the thing that I want to highlight is basically the way that you can do calibration. So what we want is this precision 10 to the -3 or better. In order to do that, people have been thinking of having a far field calibration. It's basically to have a special device that it will send a specific signal to the antenna. It will calibrate this signal. Like it's something like you are sending a signal that you know, you will detect this signal and you will somehow calibrate your instrument on real time. People have been playing with this thing on Brookhaven. They have like a toy radio telescope there in the thing, and literally they've been flying like calibrators to do these kind of things and playing with techniques to do this calibration. So this is something quite interesting. I've been helping a little bit with the basic concept, and it's basically what I was telling you. There should be some calibrator service, and now this is actually awarded. It will be in another mission in the CS4, so it will go afterwards, but it's some months after now. And then it will be sent to orbit the moon. It will send a specific packet of waveform that we know what it is. That way you will be like measuring this packet plus the actual signal. and then you can convolute, and this thing should have like a copy of template of a specific waveform that you can disentangle from the convolution, and you can actually calibrate whatever the actual antenna is doing.
But Google, you need a relay satellite, right?
Yeah.
Can you use the relay satellite to do this?
Like already existing ones, is what you're saying? No.
No, what are going to use as relay to send a signal from the mission to the Earth?
So it's a relay satellite. This is what is.
But this has to go together, right?
It cannot go together. That's the point. It's going to be afterwards, but it's going to be.
How are you going to land? To land, you need a relay. I've thought, no, that to land.
Actually, no. It is actually a lander. So it is the same concept of these things. It's basically at some point it decouples from a rocket and it goes on its own to land.
So what happens to the guy? So it decouples from something, right?
Exactly. It decouples from the rocket, and the rocket comes back.
And the rocket comes back.
This is the thing that SpaceX does.
But I thought that to land, you also need to send signals to control.
There are already things that orbit the moon and blah blah blah.
So there
are already things that
there are some relays already.
But we cannot use that one. So it's going to be sent one of them. Yeah.
It's going to be blind.
No. For landing, yeah, they can use some telemetry from things that are already orbiting the moon.
So you can use.
I don't know any details about this thing, but we can use that thing. But for doing the calibration, we cannot use that thing.
Right.
So there's going to be sent a specific relay satellite for doing the thing. And this is super interesting because really, I think that this is one of the most interesting things. If everything happens, because there's going to be like multiple ways that this thing can go wrong. But if these things happens, this thing really is a new thing that nobody has been done before, like with any radio telescope, even some on Earth. But it can be super interesting to calibrate the thing in place.
Are there plans to use this with like instruments on Earth where you can have like everything controlled, like like you can check everything before you land to touch it?
So we've been playing with that, yeah. But with super toy telescope, not with actual things like chimes, you know. Because this is not like on the actual plans of those kind of instruments, no. But we have like a really toy instrument like on site. So yeah.
Just again, how so is there the data is recorded and there's some sort of data recorder, and then how does that get sent back?
I can say about that thing. You know way more about that thing. Yeah. So yeah, there's a plan for that. I think it is still not set up. But I think they are going to they have some storage on the instrument to storage some data from I think one night. I think it's possible to do it because the thing is the data is not too much data. It's some I don't know. I think it's some megabytes or something like that because it's like a bunch of Fourier transforms. It's basically that.
Already there's some stage of calibration that's already applied.
Exactly. And then that's used to do on site. In principle, the calibration can happen like there. And then it's sent it to some orbiter. Some of those orbiters are already sent and then comes back, something like that. But something is done in place. They are thinking something like once per day, per lunar day. But yeah, I think this is not completely set. So the main thing is the calibrator status is this thing is approved. So this is quite interesting. It's gonna be sent on this CS4. So afterwards.
1 year afterwards?
No, it's 1 or 2 months afterwards. Yeah.
1 or 2 months.
Yeah, it's just basically some months afterwards. So basically it's between January and June, something like that. And remember the lander, if everything goes well, it arrives in January. No, wait. I'm saying this is the thing that happened this year. No. But the thing is this CS4 is gonna happen like on February or something, 2026. And the lander will arrive like in January 2026. Yeah.
Oh.
So if these things happen, it's quite interesting. So let me check. Yeah, more or less, I still have time to say. So one of the exciting things that we're also preparing is basically this thing of like in the CMB, the first thing is okay, you want to look for the monopole on this mean brightness of the dark ages. But for that, in principle, one of the things is okay, you will want to have like some good resolution maps of these frequencies. So the thing that we've been proposing is actually to do like the most simple thing, which is using the lessons from CMB and do more or less the same kind of technology that people do for COBE and for WMAP and also even for INEOF Planck, which is actually a linear deconvolution or a linear relation for the data to the map on these frequencies. And this is the thing that I wanted to tell you. So the reasons that we want maps, it's basically, okay, we want to gain insight about the foregrounds and all of this stuff. Basically, we want to see the galaxy in the center in galactic coordinates, that kind of stuff, shining there and actually observing in the middle because the galaxy should have some absorption also at these frequencies.
Can you mask? Can you just mask?
In principle, we want to see everything because for this, I mean, if this is not in the stage of doing like anisotropes, it's only to measure the mean temperature at that frequency. So one map will give you like 1 point on this radio spectrum.
Yes. But still, you can mask and measure the mean temperature without the galaxy.
So for extract like the feature of the true, you don't mask, you try to do another kind of thing. Yeah, I can say it, something like that, but you don't mask in principle. But you can think on many ways of doing it.
But the signal, like the contaminants that are going to come from the galaxy are like way brighter than the ones that are going to come from other areas of the sky. So like I would expect that in order to do the formal mitigation, you want to remove. I mean, I don't know which methods you plan to use to do the formal mitigation, but like I would expect to mask where the formats are going to be right there to like have better control of the formats, right?
Yeah, there should be also some masking. Yeah, but not only masking. I mean,
Oh, yeah, I don't know, that's true.
that's what I'm trying to say. Yeah.
And the calibration.
Yeah. So why mask also? Okay, you want to see stuff because this is, in principle, this is still, and nobody has detected these things. So you want to see things now. There can be some no Gaussian features. There can be point sources. There's for sure gonna be point sources. Like even planets will emit. No. And we can see things like spatial systematic on this kind of thing. So the thing that we've been doing is basically to prepare like the thing that's gonna prepare maps. And so yeah, so what we are doing is basically, okay, what are the products? So it's basically this kind of picture here. So the actual product in terms of data of this kind of thing is like correlation between 4 antennas, no? And so I think I have a better slide here. And these correlations of the antennas are basically described physically by a thing that, so by the efficiency of absorbing or emitting energy from an antenna. So it's basically the gaining power of a dielectric object, which looks like a dipole. It's basically or absorbing radiation coming or emitting radiation coming. It looks like any Wi-Fi antenna, that it works pretty similarly or something like that. And the profile of the gaining power is something that looks like that. It should be chromatic. It should depend on the frequencies. It should maybe mix frequencies and in some neighboring bands. But in principle, that should be mitigated because it shouldn't happen. But it should have some pattern, some spatial pattern, like more power coming from one side and more coming from the outside, from the other side, and it should look like something like this. This is called like the beam of an antenna. And in principle, the thing that we measure is after some amplification of the signal that comes from dipole measurements of the antenna, like the convolution of the sky, which should be like a sky brightness at some frequency with this beam of the antenna. And in principle, this convolution it's basically describing everything about your antenna and the way that you are measuring data. And these things should come out after amplifiers and all of this electronic stuff, like voltages that you can measure. It's like in optics, we measure counts of CCD photons. Here we measure voltages of the antenna. No. And these voltages are basically given by this thing. So basically, if you autocorrelate the same antenna, you will have something that looks like this. But if you cross-correlate to different antennas, the separation between the two antennas will give you like an intrinsic complex description of the signal. So in principle, we have 4 of them. We can have 4 autocorrelations and 6 cross-correlations. And these 6 cross-correlations can have like a pure real and a pure complex one. These end up having like 16 data streams that looks like something like this. in time, and it's like basically time order data, like 16 voltage measurements that evolve with time, you see, and you can represent it like something like this. So this is your data, and you want to come from this to something like this. And you know that this comes from a convolution with a beam that is basically describing your antenna. So the way that we've been doing this is we basically developed a package to simulate the way that Lucio operates, and it's basically simulating the beam of the antenna. And these have been measured in the lab because the antennas have been tested on lab. So we have measurements of what is the gain of each antenna in power. And the thing is, basically, the main part of the simulation is Lucy is basically operating on some specific spot on the moon, and it will be like rotating with the moon and moving, scanning the entire sky. So this is like a raw description of how it is moving. These are like the north ecliptic pole and south ecliptic pole. And you can see that basically by the position of the landing, it will have like a blind spot around the north ecliptic pole. And this is everything galactic coordinates. So the galaxy should be on the center here. Go ahead.
We want to combine the out and the cross correlation between the different antennas. Because I don't know much about interferometry, but like when you do interferometry, you lose the zero mode, right? So like you don't have the monopole that is what is one of the main science modes. So how are we going to combine cross mountains for antennas?
So it's basically so not in all of them you intrinsically lose the monopole. I think this is one thing that happens when you have dishes intrinsically, but not on every incarnation of a radio telescope you always lose the monopole. And I think for dipole antennas you don't intrinsically lose the information. And the thing here is basically you have the stream like the time data order data, and you want to have like the fact that this thing is scanning on time the entire sky, and this thing will cross-correlate signal from different parts of the sky. And if it can still give you the monopole, it will also give you some other multiples by the fact that it is actually scanning different parts in different times, something like this. So it's basically the cross-correlation between time and the antennas that should give you the information about the resolution in the sky. This is the thing that I want to show you, that the thing seems to be working. So the way is the simplest way. So let me see if this answers your question. So the way that we've been thinking is basically the most simple way. It's basically assuming that the data stream in time is basically linearly related to the intrinsic map that you are trying to look for. That is giving you this data stream, plus obviously some noise, because there's always noise there. No, so the thing is, we're proposing this thing of doing this Bayesian maximum posterior probability estimate, which is basically the linear, the maximum linear estimator for a posterior that basically assumes that the noise is Gaussian and the data is Gaussianly distributed. And these things are more or less well motivated by the fact that we are taking a good amount of data, because this thing will be operating like for an entire night at least. If you do this thing, if you assume that these things are Gaussian distributed, you can solve for a maximum likelihood estimator, because this is linear. You can always do that kind of stuff. In linear, it will be like somehow complicated, and it will depend like on the covariance of the noise, which is this end, and on this mode mixing matrix, which is basically mixing modes from the data in time to modes on the sky. These modes on the sky can be represented like harmonic modes or actual configuration space modes. Like you can do this in configuration space and harmonic space. And this is the thing that we've been trying to look. So the main thing is the ideas from the CMB are like, okay, you can work out the fact that these linear estimators are actually without losing information, in the sense that if you work out like the Fisher matrix from actual visibilities, which is this data stream, people in radio astronomy call this thing like visibilities. But it's what I'm telling you is basically measurements of voltage on these dipole antennas. So just in jargon of radio astronomy, these things are called visibilities. So if you work like what is the Fisher matrix of this thing with of a map that comes from these kind of methods, if you assume that everything is Gaussian, it's obviously basically conserving the same kind of Fisher matrix. when you go, there are different stages now. So you have visibilities. If you apply any kind of estimator for the map, here is a linear one. And you go from there to whatever you want. You can then from there, like put some model for for example, the galaxy, and you can fit for that model on your map. Or you can put whatever else you want. You can mask, you cannot mask and maybe try to model like point sources also. And you can fit for them from the map or something like that.
Have you already thought whether it's better to do all this component separation on the map or visibility space or?
Yeah, people have been thinking about this thing, but I think I will just concentrate on the maps and we can scale this thing. Let me just close this thing. So yeah, we've been doing this thing. People here is super familiar. So basically on harmonic and configuration space, and some early results of this kind of stuff is this kind of thing. So basically, what we do is we have this. So what is the pipeline of this stuff? So the main thing is this kind of mode coupling matrix or something that is based on coupling visibilities to maps. And this thing we are doing it like basically simulating the Lucy sky measurements. So we have some model for the means, and we basically package something that do like the whole thing of cross-correlate the modes of the sky with some specific description of the radio sky, which is basically the state-of-the-art simulations for these kind of frequencies. We try to do the thing of rotating with the moon and rotating with the earth and blah, 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 and try to see what's going to be like the actual measurements that you have. With this, we basically empirically measure this thing, and we basically use this kind of algebraic solution to have this operator that will be like the deconvolution operator. And so these are the kind of things that we obtained, and it's basically showing that you can actually have. So these things are like maps at different frequencies. This is true. This is reconstructed. This is difference. And here you have everything. So like you have like point sources, the galaxy, and at low frequencies you have absorption in the center of the galaxy because the galaxy's brightness is basically shining, but along the way there's a bunch of gas. And gas also absorbed at these frequencies, so you can see like a true here in the center of the galaxy at some frequencies, and at some others it's basically attenuated. You can see that this is the main thing that we want to see that you can reconstruct. In order to do this thing, you want some degrees on the sky to resolve some degrees on the sky, or in multiple space to go to some tens of on multiple space. So this is like the correlation coefficient between truth and reconstructed. And you can see that at least from things that we've been doing so far, you can go to of the order of tens or something like that in multiple space. That is giving you some degrees on the sky if this method is working. So we've been thinking on different other methods, but this thing probably will work well for what we want to do. So this is more or less the empirical way of saying that, yeah, you are recalling the model and something else, which is at the beginning, to me, this thing was like impressive.
You're right, and my question didn't make any sense because you're also using the baselines.
Exactly. But anyways, this thing is quite interesting. So there's just comparison. We've been playing with how to do it and putting some realistic noise on the thing and different kinds of ways to do it. And so you can see that we're still doing pretty well if you increase like you decrease signal to noise and many other different things. So
you have more information than the monopole. So why do you focus on the monopole only?
Because this is the first thing that you should do. Is basically this kind of stuff. It's because anyways, if we have more information on the monopole, the first thing that we want to do is not actually do science with this thing, but use this thing as knowing the foregrounds of your measurement. Because there's a bunch of things happening. As I was telling you, that the signal of dark ages is like orders of magnitude buried, like at least, for example, on the synchrotron radiation from the center of the galaxy. So you want to know pretty well how your instrument is measuring, like, for example, the galaxy. And many other like pointers and everything. We've been playing some other things like.
So you can also measure polarization, right?
Yeah, exactly. So
that something that's useful.
It's extremely useful because synchrotron radiation is polarized. So synchrotron from the galaxy is polarized. And with this thing, basically, the fact that these things succeeds depend on that. depend on the fact that you're using the cross correlations between the antennas.
Okay.
So there's this funny thing that if you put, there's like a blind spot, like near the northern ecliptic, a pole in galactic coordinates. And the reason why I'm just showing these things and just putting here randomly like points to be reconstructed with this kind of methods and putting a point propositally like on the northern ecliptic pole. And the fact is, so from simulations, we know that Lucy is like basically scanning the sky like this. And it should have like a blind spot. And you can actually see it more or less happening on these kind of reconstructions. So here is more or less the same kind of thing, but with actual point sources. Points is like one point at some helpix resolution, this kind of stuff. But it's quite interesting that you basically blind the point there. And you have some sort of point spread function that you can measure with this kind of stuff, which is actually the thing that the cross correlation is giving you. So yeah, this is like the main thing that I want to tell you. And so this method seems to be working, but we're actually thinking of things to do afterwards. So because this is like 20th century technologies, the thing that people used for the CMB. But nowadays we can do better. Now we can do forward models. And for example, begin with the data and try not to go to the map, but try to go all the way down to whatever model you have and try to forward model everything like the galaxy and whatever else you have. And this is absolutely possible because of MCMC methods today. We've been thinking about that, but one of the nice ideas that we've been thinking is this linear, basically the construction or reconstruction is immediately giving you like a linear approximation for the covariance matrix of the moons on the sky. So it's basically here is like the covariance between different helpix points on the sky of these maps. So this is like hundreds of something is like inside of 16 or something like that. It's like resolution of some 5 degrees on the sky or something like that. And the fact is that if you look for what is the eigenvalues distribution of this kind of covariances, you see that there are some modes that dominate over others. And this is just the reconstruction. So if you actually have some modes that dominate, you can actually concentrate on those ones. It's like doing some kind of PCA or something, but actually motivated by the linear reconstruction. And so this thing is something that can inform better, like any nonlinear method that you can think of or something like that. So yeah, this is more or less what I want to tell you. I think I crossed a little bit. So these are my super quick conclusions. So the main thing or the main message from this Lucy talk is if many things go right, Lucy will establish this viability of radio observations from the moon. And it has to be think as a Pathfinder, because it will show that you can do it. It probably won't be able to detect like the dark ages with the proper resolution that we want, but it will show that we can do it. And it probably will show that the technology that we have is viable to do this kind of stuff, and there will be some subsequent missions, no? But in principle, with the things that we have, if everything goes well, it will produce the most accurate maps of the sky on between 1 and 50 megahertz that we ever had. Basically updating things that we have from the 70s, that is like the latest data that we have up to date. There are future ongoing developments like with these map making methods. And the thing is fully funded. It will use like these CS3 and CS4 missions that you have to be done because they're basically intended for the end of next year and the beginning of the other. And both are going to be Firefly. And yeah, this is stolen from Angie. It's basically what Angie used to say everywhere. Like for the first time in his life, he's basically hoping that the project delay a little bit because this thing has like pretty strict deadlines. So it's basically that. And I can take more here.
Hugo, so
More questions for the book? Yeah.
So in this simulation where you try to recover the multiples, that's only the galaxy, or does it include the point sources or things from the solar system?
It includes everything that we know in principle. This is like some ultra, but it's a Chinese set of maps. These ultra maps. I'm not sure. Maybe you are familiar with that. It's basically in the literature what is pointed to be like the most up-to-date maps or simulated maps of the radio sky at that frequency. In principle, includes everything that we know.
It probably has point sources.
It has point sources. Yeah, you can see stuff.
And yeah, so are there things in the solar system?
Yeah. It's in the solar system. We know that there are stuff happening. There's basically whatever is plasma. I think there are planets that can have this kind of stuff, like Jupiter emits, I think. And
Yeah, do you expect things other operations on you to radio and the frequencies that you?
of course, yeah. So the main thing of developing this kind of instrumentation is making this thing blended to its own radio RFI. So it's like self RFI, and this is extremely complicated. I can say something about this, but I don't want to say it. Like the power operation of this thing is like designed to be like strictly reducing the noise for the instrument, because even the battery is noise.
And I guess like do things, even the Milky Way emission, like reflecting on the moon and.
Yeah, so the regolith. So that's the other thing. So I was mentioning it is even a nice story because on the head of the people that are PI in this thing. So the PI of Lucy is Angie, but there's a bunch of others. So in the CS2, I think, at the one that arrives someone but arrives deep on the side, there was this radio, this one dipole radio antenna that the main scientific goal was to basically measure this kind of reflection from the regolith of the moon, that it is not that well known. And this couldn't happen perfectly, but there's few data about these things. And yeah, people know that the regolith is quite complicated. So the way that people have been thinking about this thing is basically a modification of the beam on the antenna. Like you can somehow try to see this thing as gain fluctuations also on the antenna gain, but we don't know pretty well how the regolith of the moon will work. We know that it should reflect. I mean, it should be less. No, I mean it's different that ionosphere here on the Earth.
Yeah, it's not like maybe you can use whatever they use in India for the ground because of the dipoles or like, but it was used in images.
Yeah.
The problem is like you probably don't know the reflectivity of the.
No.
But the techniques would be kind of similar.
I was thinking of the whatever experiment is on the leaf.
So these things, so these things are
You have like some ground pickup, right? Like I think it's lower, but like it's.
these things are Pathfinder. So one of the things that you can gain from this, if it actually happens, if you can have an indirect detection of actually the reflectivity of the regolith of the moon. So the hope is that there were more instruments doing this kind of individual measurements, but it's quite complicated.
Is there any expectation of how their RFI is going to evolve in the moon with like kind of like what Gary asked, with like all similar distance on the commercial trees, like so that's already around.
Yeah, for now, the dark side of the moon is still not populated. So that's the good thing. So the dark side of the moon only received like one mission, just one landing, one soft landing in entire human history. So this is still pretty blinded. So this is the thing. But yeah, I think for Lucy, if everything goes well, it won't be a big problem.
The Chinese mission didn't measure any radio.
So-
The Chinese mission that landed there.
So yeah, I think I have actually the spectra from that mission. If my computer or that. So yeah, they mentioned it's basically dominated by noise, like self-RFI noise.
Were they expecting that? No, this
Um,
is some problem in the design of this.
So I think No, no, I don't think so. So I think, um, so I think this is expected, but they probably didn't expect to be like that extreme. So it's like this thing. So, um, so this is some slide like summarizing the battery challenge that the people have, which is basically self-verified. It goes to. So yeah, so this is data from the Changi landing. The Changi basically land on 2019 on the dark side of the moon is the only soft landing ever happened. So the Chinese managed to do it. So let's hope that people can do it again. So basically the thing is that you see that this thing is basically doing all of these things. And the idea of Lucy is like two-parted. There is the fact that there's this picket fence power supply. This is one of the things, but the other thing is that basically with Firefly, there's this very strong requirement that basically the lander will completely shut down after they arrive in the first night. So after the first night start, everything's going to turn down for them. So they will lose communication, they will lose everything just for Lucy to work. So this is one of the things, because this is what I think people believe that we're wrong here. Like they still have some sort of communication from the lander. So they're still using like power from them, not from the things that were mentioned, like the ratings.
It's pretty exciting.
Oh.
So CS1, CS2 failed. Your CS3. Hopefully CS3 and CS4 will work.
Yeah, no, but
That would be great.
yeah, so yeah, this is
Okay. So I don't see any hands, so that's thanks. We come back at 11:30. Is that okay? That's a short break. I wasn't ready.
I tried.
Yes, eu sei que tinha dinheiro do departamento. Só que eu vi
Sim, do
I think, you know,